With those examples, you see how diverse these rules can be. But you probably also see how powerful these SDN routers can be, right? It can emulate the traditional forwarding, just like the traditional routers. It can do longest prefix match, okay, and forward it out on a particular interface. It emulates also a link layer switch, so matching on the destination MAC address and then forward the packet further. It emulates also firewalls, okay, by looking up the source IP address or destination port number and then dropping the packet or allowing the packet. Yeah. One additional emulation SDN can do is this, netbox. Because what? One of the actions allowed in generalized forwarding is this, changing the content in the packet. So netbox there, okay, when there's packet coming from the local network, before you send it out, what do? We replace the source address and the source port number. So we could rewrite, okay, specific address and port number, okay, according to the need. So SDN, okay, is a very general machine that unifies, okay, a number of these different devices that we need, okay, running from the network layer and below. The last example is actually to go beyond one single SDN router to have multiple of them and forming a network like this. Okay, so you see here, this network, okay, is composed of 3 SDN routers, S1, S2, and S3. And then for each of these, talk to the controller through the Openflow protocol. Right? So this controller here sometimes being also called the Openflow controller. Just like the SDN routers, okay, some of them will actually call them the Openflow routers. A scenario is this, let's send packets from H5 and H6, here and here, okay, from subnet 10.3 to H3 and H4, H3, H4, subnet 10.2, okay, but through a very specific route, okay, from S3 here through S1 and then reaching S2. So yeah, we want this path. Now, the reason we want to do this in SDN is this. In traditional routing, the routing algorithm usually gives you this, okay, if you want to send data from 10.3 subnet to 10.3 subnet, because this is only one hop, okay, this is the shortest path. Traditional routing does not provide you the flexibility of, manually configure a specific route. But hey, luckily we have the Openflow controller. So Openflow controller can actually manually configure these flow table entries to S1, S2, and S3 to allow a specific path, S3, S1, and S2. And these entries will look like this. Okay, inside S3, the flow entry will look like this. Source being from 10.3, destination being to 10.2. That's for the packet on interface 3 here. Now the entry in S1, this router at the bottom, will look like this. If the ingress port is 1, so this is incoming port number being 1. Source 10.3, destination 10.2, that's forwarded down this interface 4. And then we manually configure S2 flow entry looking like this. Ingress port being 2. Yeah, so the packet is definitely coming in from here. Now, we need to separate the traffic so that it goes to H3 and H4 correspondingly. Alright, so these are different IP addresses. So if we match more exact, the destination address being 10.2.0.3, then go on interface 3. So data go this way. On the other hand, if it's 0.4, then forwarded on interface 4, therefore reaching H4. So Openflow, really nice and flexible. So something to add is just here. Traditional routing implements a routing algorithm. You know what? Yeah, the controller can actually run a combination of manual configuration plus the routing algorithm. So it's a lot better, a lot more configurable, a lot more flexible than the traditional router. Alright, so that's chapter 4. In the overview, we learned the separation of the control plane versus the data plane. Two models, okay, working the control plane. Traditional one doing route algorithm on each router. Newer one running routing algorithm centrally on a powerful server that is not, okay, the router, outside of the router. In the data plane, also two models. Traditional destination-based forwarding versus the newer one, okay, generalized forwarding. Yeah, section 4.2, we learned about the inside of a router, right? So there are these input queues and output queues. You need to manage these queues. We call that the buffer management. Okay. There's the switching fabric in the middle. There are different architectures. Something extra in the router is this, in the incoming interface. Yeah, there's a table lookup process there. Okay. In that we do longest prefix match, okay, for the traditional forwarding. 4.3, pretty long. Okay. Essentially, most of the content there is about IPv4, the packet format, and how we do fragmentation and reassembly in IPv4, and how we address, okay, particular interfaces using a 32 address space. And hey, in the 32 address space, there's a certain part being the subnet, okay, things like that. NAT, okay, this is related to IPv4, but you can also do this on IPv6. Okay. So NAT and IPv6, these two topics are more to address this issue. 32-bit IP address space in version 4, not good enough, okay, too small. So IPv6 use a longer address space, and NAT use a translator service, okay, to address the issue. And yeah, just today, 4.4, generalized forwarding and SDN. So you see here, the matching rules can be very general, and the actions can also be very general, unlike the traditional forwarding. And then we see a number of examples for these entries in the flow table, as well as a network example. Yeah, the next question to ask, and I think Pei An asked it early. Okay. How does one decide what the forwarding table and the flow table look like, right? So, hey, how does the control plane, does the routing computation or combination of route computation and maybe some other preferences so that we could set up these forwarding table and flow tables to install to the data plane of the routers? Yeah, so the answer is the control plane is doing it, and that is chapter 5.